Hello, hello, hello. Hello, hello, hello. Hello. Okay. Is that no mic? Hello, no mic. No people. Can move front. Can move forward. Okay. So finish revision or not? Huh? No. Special revision. Probability. Okay. Okay. Yeah, good luck. Okay, so we continue with continuity. Continuity. Huh? But let us continue with continuity. Convolution. Yeah, let's continue with continuity. Okay, so let fxy ready. Yeah. Okay, let fxy to be a function of two variables. So what does it mean to be fxy is continuous at a point? Yeah. What does it mean to be continuous at a point? The limit of f would the point have to equal to the value of the function at that point. Okay. So uh so in one variable case, if you have limit approaching to the same point, your f have to attain the value. Okay. So you can imagine this picture in 2 dimensions or 3 dimensions. Okay. So the limit have to equal to the value of f. Make sense? Okay. So let's do one example. So where's the following function continuous? So this function is defined piecewisely at the point that is not the origin, it is 3x squared times y over x squared plus y squared. It is 0 at the origin. Okay. So where is this function continuous? Where is this function continuous? Huh? What is 3x squared times y over x squared plus y squared? Polynomial. Okay. Product of polynomial. Quotient of polynomials. Okay. Where are these polynomial continuous? Huh? Polynomial is continuous at everywhere. Okay. Product of continuous function is still continuous. Okay. But there's a quotient here. When does the quotient continue? Point and set 0. Not quite. Except the denominator not equal to 0. So when does the denominator equal to 0? Yes. When x y. Yeah, when xy equals 0, right? Okay. Because we are adding two positive numbers. So only 0 plus 0 is 0. Okay. So there's one possibility where 0, 0 is not continuous. But I define the function to be 0 at the origin. So is this continuous? Try and show it. Yeah, try and show it. See if the limit of f agree with 0 or not. So you need to answer whether it's continuous or not, right? You need to go back to the definition. Show that the limit of your function is equal to the value of the function at that point. Try show. Yeah, try show this. Compute what's the limit of your function. Yeah, so what's the limit of this function here? For those who haven't got your midterm mark, right, you can email me. I can send you the mark on paper. What's this limit? Huh? 0. Okay. So this limit equals 0, meaning you go from nearby origin, moving forward to origin, you got 0. Okay. And then your function is defined to be 0 at the origin. Okay. So they equal. So by definition, f is continuous at the origin. Okay. Okay. How about this one? You try. Right, this function continuous. How we calculate the limit actually? How we calculate the limit actually? It's the sine one measure. Yeah. Yeah. How we calculate the limit? Yeah, like this. Uh, so this one, wait, okay, so this limit converges to 0, right? It's because actually because of the dominator, the numerator converts faster than the denominator. Because you take product of corner number. I feel like we don't have L'Hopital rule for two variables. But then check if we can have more specific method to see. So do which question? Do this question. Yeah. So for this question, I searched already. There's no L'Hopital rule for multivariable. So one way we have used last time is the polar coordinate. I use polar coordinate. Okay, how about this one? Is it continuous at origin or not? Why? What does that? Why? Cos square times sine square, sine theta. You okay, so you make it into polar also. Okay, so let's try it. So we need to study the behavior around the origin. So away from the origin, it is continuous, right? It is continuous at R. Throw away the origin. Okay. Because it is a rational function, and the denominator is not zero. It's not a zero function, or not zero. It's not zero. Okay. So let's check what happened nearest to the origin. So if you use polar coordinate, what happened? You get R squared cos squared theta minus R squared sine squared theta over R squared, which is equal to cos square theta minus sine square theta. Okay, so if you put different theta, you will get different value. So meaning it depends on the path you take. Okay, or that's one easy way to see why the limit is not zero. What path you can take? Pick two easy paths. What's the two easy choice you can pick? Approaching x-axis and approaching y-axis. Okay. So if you approach from x-axis, what do you get? You get fx0, which is x squared over x squared, which is 1. And then if you approach from y-axis, you get 0, y, you get minus 1. Okay. So I have plotted the graph out. So what's really going on here? Okay. Yeah, so this is the x squared minus y squared over x squared plus y squared. Okay, so if you approach y-axis, you see approaching y-axis, right? This is the y-axis. Where's the point? They go to -1. Okay, if you approach x-axis, Okay, x-axis here. Okay, all the point go up to 1. Okay, so if you go in different path, you get different value. So you cannot fill in the hole in the middle. Okay, because in the middle there's only 1 point. You cannot put 1 and -1 at the same time. Okay. Okay. So if you are pedantic, right, here actually there's no fill here. Nothing here. It's empty here should be. But to make it look nicer, they fill it in the color. Okay. Yeah. Yeah, center is empty. Here should be empty one. Here also empty. This part here. So the graph keep approaching the origin, but never touch. Okay. Okay. So you can see that if you go from different path to origin, you reach different number in different value. Okay. Right. Okay. So we should start new section. Partial derivative. Okay. What's derivative to you? What's derivative? What's derivative? Tangent. Tangent, tangent at the point. Hey, hello. Testing. Thank you. Testing. Okay, so what's tangent? What's tangent? Slope. Okay, slope, sure. So I mean, geometrically, why is this a tangent? Why if I draw something like this, is this a tangent? Why this is not a tangent? Not quite. Not quite. Okay. So how to make sure what we draw is a tangent? Okay. So how we start? So okay. So first of all, we know how to find the gradient of a straight line. Okay. So do you know how to find a gradient on a straight line? Y2 minus y1 over x2 minus x1. Okay, so this is what we define. And you can see that this number, right, is not affected by what y2 or y1, x2 or x1 you find on this line. Right? Any y2, y1 will work. Okay, for the line. Okay. But on the curve, we don't have this line. So where do we find the line? So we find nearby point to create this secant, this straight line here. Okay. And then we can see that when we choose closer and closer point to the tangent point we want to find, this straight line actually approaches the tangent line. Okay. So we are really taking the limit of this straight line. Okay. So derivative is taking the limit of this line. Okay. Until we reach the single point. Okay. So you can see here. So the partial derivative definition is f of a plus h. Okay. You compare to the next neighboring point with the point that you want to draw the tangent line divided by the change. So you get the point closer and closer to h, and then until it reaches the point itself. This is the limit. Okay, this is the limit. Okay. Okay, so when you take in limit, all right, you see, partial derivative is the limit of some special function. Okay, this special function here give you the slope nearby. Okay, they give you the slope nearby. Okay, and then you're taking the limit when the h decrease into a single point here. Let us call it AB. Okay, go to 0. Okay, so you can imagine that this slope here limit to a tangent line that you want. Okay, make sense? Okay. Okay, so for partial derivative, right? So you have now in one variable function, you only have one variable, but in two variable function, you have two variable. You have two direction. Okay, you can make these changes in the x direction. You can also make the changes in y direction. Okay, that's why we have two partial derivative here. Okay. 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 So one, you make increment. You study the increment in x. The other, you study the increment in y. Okay. This is just classical definition. You don't need to work from here. Later, we'll tell you a tool to calculate. Okay. And in general, you can form a function for your partial derivative. Okay. Function. When you consider all the point A, B, it becomes a function. So there are a lot of way to write partial derivative. If you see these in the literature, they are the same. Okay. For example, f subscript x is equivalent to del f del x, or del of f with respect to x, or sometimes we put del z del x if we call our fxy to be z, or sometimes we call d1f. Okay, so we have two variables, right? X and y. Usually we call the x to be 1, y to be 2. Okay, or we just put a capital D subscript x. Then these are different notation here. Okay, so how to find partial derivative? So this is the rule. You don't need to work from the definition of limit. You just start from here. So how to differentiate partial differentiate? So there are two variables in your function. Okay. So if you want to differentiate with respect to x, you need to treat the other variable as a constant. Okay, and then differentiate with respect to x. Similarly, if you want to differentiate with respect to y, you just treat x to be constant. So let us try one example here. So the function is fxy equals to x squared y plus 3y cubed. Okay, so let's say we want to differentiate f with respect to x. Okay, so there are two variables here. Okay, so how we treat a y variable, we just treat it as a constant. Okay, so we have to differentiate x squared y with respect to x. Okay, so y is a constant. You need to differentiate x squared, you get 2x. Okay, so altogether you get 2x1 for the first term. For the second term, what do you get? 0, because you treat it as a constant. Okay, there's another thing I use here, right? I use that this operator is actually linear. Okay, so I can differentiate term by term and then add them up. Make sense? Okay. Okay, so this is our fx, xy. And how about differentiate with respect to y? What do you think? What do you get if you integrate with respect to y? So you treat x squared to be constant. Okay, so what do you get? X squared from the first term, 9y squared. Okay, good. Okay, so the question also asks you to compute what is fx and fy at the point 1, 2. Okay, so what you do, you just substitute the point into your expression. Okay, so fx 1, 2 is 2 times 1 times 2, which is 4. And then fy 1, 2 is 1 squared plus 9 times 2 squared, which is 37. Okay. Okay. How about try this? Try this one. Try this example. Z equals to x squared times sine of xy squared. So what is the partial derivative with respect to x and y? Okay, so when you differentiate with respect to x, what do you use? Huh? Product rule. Okay, so you use product rule. So first term you get is 2x sine xy squared. Okay, plus, is it correct? Okay, so how about the second term? S squared times cos xy squared by chain rule, you also get the y squared. Okay, good. How about next? So there's only one function having y variable. Okay, so you treat other thing as a constant. So what do you get? You get x squared cos sine y squared, and then by chain rule you get the constant 2xy. 2xy. So altogether you get 2s cubed times y cos xy squared. Okay. Okay, so you know what's the meaning of these 437 and these partial derivative? What's the meaning of this? Huh? So when you evaluate this function, this partial derivative at the point, meaning at that point, you have a slope of 4 or 37. Okay, slope of 4 or 37, you know, right? Y equals to 30. Y equals to F for X. Correct or not? Okay. So when we present the partial derivative as a function, meaning this function, if you put in number, I will tell you what's the slope at that point. Okay. So when we put input a point into a partial derivative, it will give us a real number. Okay, this real number tells me the slope at that point. Okay, how slopey is for the tangent line. Okay.
What does it do with the respect to x?
Yeah, with respect to x and y, what is that? Let me see we got example or not, then I will show you that example. Yeah, we got example. Okay, we got example. Let me show you the example. Okay, yeah, so very good question is you got two number, one is with respect to x, one is with respect to y. So what are those numbers representing? Okay, so like what I said just now, the partial derivative of f, a, b are the slopes of the tangent to the curve C1, C2 at the point A, B, C. So what is C1, C2? So you have a surface. Okay, suppose you have a surface, right? So you want to differentiate this surface with respect to x and y. So what is C1? Okay, so let's say we want to find partial derivative at this point. You want to find tangent at this point. Okay, so C1 here is the curve that is parallel to x. Okay, in the direction of x. Okay, C2 here is the curve that is parallel to y in the direction of y. Okay. Then the partial derivative we found here is the slope of these 2 points, these 2 tangent lines. Okay. Let's see this example here. Okay. So suppose fxy is equal to f 4 minus x squared minus 2y squared. Can you find what is first derivative at 1? Yeah, try and find what's the number first, and then we will try to interpret this number geometrically. Okay, I think this derivative should be relatively easier than the previous one. Okay, so what's the first partial derivative with respect to x? Huh? What's this? Negative 2x. Okay, how about with respect to y? Negative 4y. Okay, good. So evaluate at 1, 1, what do you get? Negative 2 for the first one. Negative 4 for the second one. Okay, good. Very good. So, what are these slope actually, right? So let's draw out the tangent, slope of the tangent line. So the first one is z with respect to x. Right? Z with respect to x. The slope is negative 2. Okay, somewhere here. Negative 2. And the other one is z with respect to x, y. Okay, and then here you also have negative 4. Negative 4. Okay. Hello. Yeah, negative 4. Okay, so how do we put this into picture? Okay, so let's look at the picture below. So this is the 4 minus x squared minus 2y squared. Okay, this is this a plane? This is not a plane. Okay, this is something else. But we have drawn this surface out. Okay, so how we interpret this number? Okay, let's see where it is 1, 1. Okay, where's the point 1, 1? So when we found this point 1, 1 in the domain, we map it up to our surface. Okay, so let's say this is the 1, 1, the point 1, 1. Okay. Okay. So in the direction of x, okay, the surface curve in this way. Okay, there's a tangent line here. Can you see that this diagram here is actually represent the slope here? How? Yeah, right. Okay. So you have to match up the axis. Okay. So this axis here is facing up at the moment. So you need to turn this diagram around. Okay. And then match up the z-axis. And then you will see that this line here is actually this red line here. Okay. Meaning that if you stay on this surface and then you go as the x direction, it go decreasing. Okay, decreasing from the origin to positive x. Okay. Similarly, for the direction of y, okay, what happened? If you go the direction of y, because y is facing to the left, right? Okay. The slope is also decreasing when y is increasing. Okay. I think this is easier because it is directly matching up with this diagram here. Okay, but this one you need to turn around. Okay. Okay. Any question or not? Okay, so far so good. Okay. So far so good. Yeah. Okay. Or sometimes we can interpret partial derivative as an instantaneous rate of change. How about do this one? Okay. So we will see the implicit differentiation again later, but let's recall how to do this. So what is this? This is the level surface, right? Level surface. Okay. On the left is a function. Okay. But you let that function equal to some constant. Okay. So you cut it. This is not quite level surface, right? Because you have 3 variables. Okay. If you define as a function, then you have 4 variables. Okay. So if you cut 1 dimensional, you have 3 dimension. Okay. So this is a level solid. Level solid. Okay. So how to do this? Okay, how to do this? So if you want to do implicit differentiation, so you want to differentiate the whole thing, okay, with respect to x, for example. Okay, so what we are trying to do is we want to extract what is del z over del x and del z over del y. Okay, this is what we want to extract. But you can see that this z here, right, is in terms of xy. Okay. But the problem is we cannot just write z in terms of xy because we have z cubed here. Right? Okay. Usually, right? Usually if we can write z equals to, for example, x plus y minus 1, okay? If we want to find del z, del x, we just simply differentiate the right-hand side, okay? But in this case here, we cannot express a single z in terms of other variable. Okay, that's why we use implicit differentiation here. Okay, so in our mind, we know that z can be written as variable of x1, but we cannot really just express a single z in terms of the other. So what we have to do is we use implicit differentiation. Okay. 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 So what am I saying here is Z here, the Z here is really a function in X, Y. Okay, Z is a function of X, Y. Okay, so we use the property of partial derivative is linear, so we can break out the sum. And we break out the sum. So 6, 3yz is equal to 0. Okay, differentiating constant is 0. So you partial differentiate x cubed, what do you get with respect to x? Partial differentiate x cubed with respect to x, what do you get? 2, 3, 3x squared. Okay. So y cubed, you treat y as a constant. So you get 0. You treat z as what? Variable in xy. Okay. So you need to use chain rule here, right? Because you need to use chain rule here. So what's the chain rule? 3z squared times del z del x. Okay, chain rule. Okay, you need to use chain rule here. How about the next one? Product rule. Okay, good. Product rule. So product rule, what do you get? 6yz plus d6xy del z del x. Correct or not? Chain rule. I think it's correct. Okay. Yeah, I think it's correct. Okay. So in this case here, yeah, good. I think in this case here, you see, del z del x drop out. Okay, now you can collect the del z del x now. So let's collect the del z del x. 3z squared plus 6xy times del z del x equals to minus 3x squared minus 6yz. Is that right? Yep. Okay. So in this case, our del z del x is just minus x squared plus 2yz over z squared plus 2xy. Okay. Yeah. Okay. Okay. Yeah. Straightforward. So far, okay. So far, so good. Okay, maybe I let you try this. Let's try. What is del z del y? Try and compute del z over del y. Del z over del y. Yeah, try compute what is del z over del. See if you get this final answer. So let me copy what's the function. X cube plus y cube plus z cube 6xy z. Okay, have anyone tried? What's the first line you get? What's the first line you get? Huh? 3y squared plus 3z squared del z del y plus 6sz plus 6xy del z del y equals to 0. Okay. So if you rearrange this equation, you should get the similar answer. Okay. Actually, can you observe something here? Yeah, symmetry. Because the original function is symmetric in x and y. If you see, if you swap the position of x and y, you still get the same formula. Okay. So you can see that this differentiation here, if you swap x and y, you will get the other answer. Okay. So this is one way to guess your answer. This is one way to guess your answer. Okay, so let's take a break until 9:06. Who is beside Teresa? Jiaming. Yeah. Last name eh? Liu. Liu Jiaming. Liu. Liu. Yeah. Jiaming. Jiaming. Last 3 digit eh? 608. Oh, Chia. Okay. Okay. Who is behind Jiaming? How about you? Yeah. Wang what? Oh, Wang Yuxuan. Yeah.
我家写的奇奇怪怪的点，
什么叫奇怪？它不奇怪。
那才不。
哦，不可以，我等一下要解释这个东西，不可以，因为它这个是 partial。等一下我解释一下，奇奇怪怪。 王宇轩。how about the 给我看一下。所以他一个抓住啊，应该就结束了。Who is beside 一顺啊？Who is the one beside 一顺？陈玉玲啊，陈玉玲。陈玉玲。不用，我们就看他的，然后我们就转问后，至少以后有个气氛的对，你不知道，需要选一个更高的欢迎。所以就他的口水分到来这里。什么？这个是前面才发挥的快，你出来啊！你站起来，你没有讲错啊。对。对的，三个。他一定会有是30，一定会有钱吧？不要说了。那边是在哪个？他不给，因为他们有一个给。对吧？错的，但是有些深度表是以外，然后我们这一次是 Hello。你看到是？看来我可以抄抄别人。你看谁在喊这个字？你不会做，跟一直白纸换。不是，因为我有这种我们讲这个很难理解，很理解。我没有听。喊个一起要一样的。我觉得不能讲，好少不是放在他头上，我呢是这样子放的。哎，是不是你帮我们点了？对，天哪！那我那能给你。 他们讲我没有写，我就看你不客气。然后那叶子你看到我家，喂，不要。他拿后面的后面看着你，这主席有些记起来了，你要知道你到你会发现东西我不重要，要写就是那个是你，对啊，你把这个那同事个就是前四个有题了，他问你那题这么你什么？我拍到你那题啊，他跟我讲什么东西都可以逃里面的，但是后面那个，然后我还讲，对吧？我直接跟我讲什么东西都可以逃里面，然后就问他说，请看那里对，然后我一直问不要哪里，没有事。你漂亮，什么东西那已经基础了，不要讲已经忘记了，过来过来。Okay, hello. Hello. Okay. Can I start? Hey, got sound, no? Got sound, got it? Okay. Okay. So I put this del notation, right? I don't put, huh? Yeah, I also can't hear myself. Huh? Don't use mic. Seriously. Don't use mic. Okay. Okay. Don't use mic. Hello? Don't use mic. Okay. Okay. So yeah. So why we put this del notation, right? Instead of D. Right? Previously use D. Because del here, you are telling people that in my Z, I still got other variable. Okay. If you use D, it means that you only have one variable inside. Okay, you just differentiate with respect to that variable. But use del is a partial. There's other variable inside my function. Okay.
Just the convention, right?
Not convention is a definition. Okay. Convention is when we say convention, it's like it's a practice, but this one is kind of fixed because there's meaning to this del here. Del here, when we put del, meaning there's other variable inside. We only differentiate with respect to one variable. Okay. When we put dz over dy, that meaning my z is just function in y. Okay. Later you will see that these two notations appear together. Yeah, they appear together. So you need to know what function you are differentiating. Okay, they will appear together later. Okay. All right. Okay. So should we go to the next one? Okay. So you can do first derivative. You also can do second derivative. Okay. 加起啊。Okay. So second derivative. So you see now second derivative you have more combination. You can differentiate with respect to x first, and then you differentiate with respect to x, or you differentiate with respect to y. Okay. Or you start with differentiating with respect to y, and then differentiating with respect to x or y. Okay. So there are four possibilities. Okay. You could do xx, yy, xy, yx. Okay. There are four possibility when you do second partial derivative, right? 2 times 2, right? So 4 possibility. Okay. Yeah. Okay. So let's try find the 4 second partial derivative of this function. Okay. Let's try to find 4 of them. So let's start with finding the first derivative first. So f x and fy. Okay. So what is fx? Differentiating f with respect to x. You get ey minus 1 over y cos sine over y plus 3x squared y squared. Okay. How about with respect to y? You get x e to the power y. So you get the chain rule. What's the chain rule you get? Plus 1 over y squared cos sine over y plus 2 times 3 cubed y. Yes, that's right. Right. Okay. Okay. Now you need to do the 4 possibility. Where? 4 over y squared. Do you have x? Yeah, you should have a x. Yep. X is a constant. Yep. Okay. So now what is fxx, fxy, fyx, and fyy? Okay. So fxx is differentiating fx with respect to x. Okay. So meaning you differentiate f twice with respect to x. So let me get this away. Okay. So you differentiate again. So you get 1 over y squared cos, sine x over y plus 6x y squared. Okay. Depend on what the question is asking, right?
If I misunderstand the question by 4 seconds into 4 seconds, then
Huh? Why are you asking? You misunderstood the question 4 seconds into what? Huh? Oh.
刚刚我就是以为你要我4秒钟。
You're too creative. Too creative. Okay. Yeah. Yeah, so you need to like understand the context first, right? You do okay. Your problem is like you read until here, you stop already, find the 4 seconds. No, you need to read the whole context first. Okay. Yeah. Okay. So fxx is this. Okay, I leave you to find what is fxy, fyx. And then later we check. What is the other 3? Let me take some more attendance first. Compute all of them. I think there's a miracle inside. Yeah. I don't know. You try first.
Oh, you know,
What you know? Hey, who is the guy just coming just now? Who are you? Who are you? What's your name? Here? Lian Ye. Oh, okay. Thank you. Lian Ye. Finish compute already. Start talking already. Finish compute. Already. Already. Okay. Wait. Wait. Let me set up. Hey, okay, so be careful with this notation. Be careful with this notation here. So when I write fxy, right, do I mean differentiate x first or y first? So this is convention already. So I want to put the one that I differentiate first inside or outside. Okay. So by convention here, I put the one that I differentiate first inside. Okay. So meaning if I write fxy, the one that's closer to f I differentiate first. Okay. So I differentiate with respect to x first, and then I differentiate with respect to y. This is convention. Because convention can change. I also can say outside first or outside first. Okay. But I think more natural is this way because you can see that these two actually match up. Okay. So you are differentiating y of fx. Okay. 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 So so in this case here, we are differentiating with respect to y of fx. Okay, so what? So Rainy already finished, right, Rainy? So what do you get? Not yet? I thought you finished already. Is it confusing when you see this x and this x or not? They are not the same x. I mean, xy here are points. Okay, x is the direction. Okay, so they are not the same, really the same thing. Which one? A. Which one? Which one? This one? This one? No, no, no. They all are x. Meaning, for example, I can also name this as FMN. What? Uh, depend on how they name the x-axis and y-axis. Depend on how they name the x-axis and y-axis. X-axis and y-axis.
Can I say that the outside one is for all x, then the inside one is for
That one is wrong. That's what I'm saying.
That's wrong.
That's wrong. The outside x is just the x direction, not the point. No point. Here, okay. This x, right, is x direction, not point. And then here is point. Okay. So they are not different x. I also can change my function into mn. So fxmn if you want. Yeah. Okay. 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 Who finished computing this? Fxy. What do you get? EY. E power of y plus 1 over y square cos xy. Cos x over y plus minus okay, x over y cube. Okay, sine. Sine sine x over y plus 6 x square y. Okay, let's check this. Okay, so let's check this. So we differentiate fx with respect to y. Okay, fx is here. Okay, fx is here. So we differentiate the first term with respect to y, we get ey. Correct? We differentiate the second term with respect to y, we need to use product rule. Okay, product rule. So product rule, we differentiate the first term, we get 1 over x squared, correct? And then come up with a sign. So the sign cancel out, get positive. The second term, we need to differentiate cos x over y. So to differentiate cos x over y with respect to y, we need to use chain rule. Okay. So you differentiate cos, you get minus sine. Okay. But when you differentiate using chain rule again, you get minus 1 over y squared. So minus, 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 still minus. Okay, 3 minus. Okay. And then lastly, we differentiate 3x squared over y squared. We get 6x squared over y. Okay. So let's see another miracle here. So the miracle is fxy equals to fyx. So let's see, is it true? So we have fy here. We want to differentiate with respect to x again. Okay, differentiate fy with respect to x. What do we get? For the first term here, you see, you differentiate x ey with respect to x, you get ey. Okay. And then you differentiate the second term with respect to x, you need to use product rule. Okay. So our first term drop out 1 over y squared cos x over y. Okay. How about second term? You differentiate cos x over y. You get minus x over y squared, y cubed, because the constant of x is 1 over y. Okay. But you differentiate cos, you get sine 3 over y, minus sine, I mean. And then plus, you differentiate x cubed, you get 3x squared, which in turn you get 6x squared times 1. Okay. So you can see that these two functions are the same, but how you found them is different. Okay. So this is the magic of mathematics. Okay. So you could have different way, but match up in the end. Okay. Huh? No, no, this is like how you discover something, right? Okay. Yeah. Okay. So later we'll see that this is actually not a miracle. Okay. So what is fyy in this case? So you differentiate fy with respect to y again. So what do you get? You will get xey plus what? Plus what? Plus minus 2 minus 2y negative 2y x over y cubed, is it? Yeah, let me write out my answer and then check. Okay, do you get this? fyy. Ah. You get this? Yes, ah. Same or not? Is it same? Let me check. Color white. Okay, so you think this one is wrong? So I differentiate this term here. How to differentiate this term? Huh? Let's check. So we get minus 2xy minus 3. Yeah. Eh? Yeah. Okay. Okay. So far, okay? Agree? Okay. Everyone agree already? Okay. Got it? I mean, got it already or not? Already got it? Okay. Okay, move on. So by this clearer theorem, we know that if both fxy and fyx are continuous on a, if you don't like this open set, right? You can think of this as a disk, open disk. You know open disk? Okay. This, yeah, open disk. Okay. How about you just think of this? This you know, right? Yeah, CD. We don't want the hole for now. So we want the circle filled in. Okay. No, it's a disk, it's a disk. So like xy such that xy minus some point is less than or equals to c. Okay, c is a number, is the radius. Remember last time we have this a square b square equals to 1 circle center center at 0 with radius 1. Okay, now we want to fill in the circle. We call it a disk. Okay, yeah. So it's a constant radius from 1 point. Okay, so if this hole, then fxy equal to fyx. It's kind of amazing. Why amazing? Because you talk about continuity, but you can infer something on the function. The function is the same, just because they are continuous. Okay. Yeah. Okay. Yeah, I just want you to appreciate. You don't need to know why it's true. Okay. Yeah. 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 Okay. So the next one is yeah, how you appreciate this if you count, if you know that they are continuous, then you straight away compute one of them is enough. If you happen to know it is continuous. Okay. Yeah, if you happen to know. So next is you can extend this part.
So I can use this to prove continuous.
No. I mean, this is one direction, right? Continuous imply equal, not equal implies continuous. Yeah, so cannot. Yeah, only one direction. Yeah, one direction. Okay, so we can extend the definition to 3 variable, 4 variable, 5 variable, 6 variable, 10 variable. Okay, so if your data set form a continuous subject object, then you can do this partial derivative. Okay. Right, if your data set form a continuous set, then you can use this. So higher order partial derivative we call mixed partial derivative, such as this. So if you mix the direction you differentiate, we call it a mixed partial derivative. Okay. So this is some extension. You want to do this or we can skip this? Do this. Okay, try. Yeah, just extend to the 3 variable and then compute. What is fz, fy, fz? So if you are free, right, you can compute up to second derivative. So how many second derivative here? 8. Yeah. 2 to the power 3, yeah. 8. You got xx, xy, xz, yy, yx, yz. Hey, more than. Oh, 6, 8. Wait, let me write down. Yeah, wait. X, Y, Z. Yeah, 3 times 3, right? Yeah. No more. No more, right? Triple. Yeah, third derivative. What's the reason? The reason is you can imagine something like power series and power series. So power series, you only consider f prime, right? Okay, so in this case, we also can consider three-dimensional f prime, prime. Yeah. Okay, I think fx, fy, fz are easier. Who is behind for me? Not behind this side. Like call thing. What? Call willing? Oh. What? Okay, so do you get y plus 3z for fx, and then x plus 2z, and then 2y plus 3x? Do you get this? Okay, so what can you observe here? Fx and Fy, you just swap x and y, you get the same answer. Right? Because your original equation, if you swap x and y, you still get the same equation. Can you see it? Can see or not? So for the original equation here, right? If you swap the position of x and y, you also get the same equation. Okay? So this will imply that this fx and fy is the same up to swapping x and y. All right. So if you swap y and x, you get the other one. Okay. Yeah. Not magic, this one. It's not magic. Very magical. Yeah. Okay. Yeah, one way to see your answer. Okay. So you can see the symmetry comes into calculus. Okay. Okay. This one. This one. This one want to skip or skip or do? Want to do this? Do Okay lah, do lah. Huh? What? Okay, do. We can go slower today because no one here.
You know what?
Less people here. Can go slower.
You skip this.
How does it make sense?
Huh?
It makes sense.
How that makes sense? That makes sense. Just I want to skip. I just want to do. Okay, do this. So what you have to compute first before computing this second derivative.
First derivative.
Okay. First derivative with respect to x, w, and z. No need to find y, right? You don't need y. Okay. So find what is first derivative with respect to x, w, and z. Huh? Yeah, because you see, increase again. 4 variable now. 1, 2, 3. Yeah, 4 variable. Please. So yeah. In principle, you have 4 of them. Yeah. Yeah, in principle, you have 4 of them. Yes, this is a 5D graph. How to imagine 6D? 60. Not total, 60. 60, if you cut into half, you can see the cross section in 3D.
You calculate 60 the total.
Total,
Can calculate one.
later after class we can calculate. Huh?
是真的 probability 是多少？
I don't know.
我先，
Do this first.
我先。
不是。No, here is 4 variable 4 variable. Yeah. Hey, 4 variable, any symmetry here, straight away check. If you swap W, X, Y, then all get the same. Yeah. Okay, later you can observe. No, no theorem. Don't use the sim. Hey, in the class, don't write by symmetry. Then this is I mean extra stuff. No, exam cannot use symmetry. I'm just providing you a way to see. When you
Exam, you serious or what? Exam I cannot write by symmetry.
Cannot. Why? Huh? Because we didn't prove it.
Why, right? That one hot one.
That one polar coordinate we can set one.
Polar coordinate.
By symmetry I can multiply by 60.
Oh, that one,
I prove because I can see it with symmetry.
Yeah, that one we kind of assume you can do. But here not assume. Yeah.
So you state in the exam lah.
Huh?
Proof without by symmetry.
No. I'm just providing extra way for you to see. So when you compute the derivative, you still need to start with differentiation. Okay, del t del x, you get z times 2x of e to the w squared plus x squared plus y squared. Yeah, I mean, so what I tell you is true, right? But you know, in uni, right, they have this system. So sometimes this system, I don't know if it's good or bad, but you need to have some uniform way to test everyone, right? And so you cannot include everything inside. So it is good for your future, but you are inside a game, so you need to play the game rule now.
And then it's very sad.
That's very sad, huh? I also think that's sad. But this is no choice. Okay, differentiate t with respect to w. You also get z times 2w e to the w squared plus x squared plus y squared. Differentiate with respect to z, you get e to the w squared plus x squared plus y squared. Okay, so how about the next level? So we differentiate. Which one product rule? Where got product rule? Where got product rule? Z E is not a function in terms of that. What product? If you use product rule, you also got 0 for the other term because it's not a function in Z. What's your name? Huh? Yeah. Yeah, what's your name? Huh?
Yeah.
Oh, okay. Okay. It's okay. Okay. So how about differentiate tx with respect to w? You get 2w z times 2x e to the w squared plus x squared plus y squared. which is 4wzx of E. Yeah, not enough space. 4wzx e to the w squared plus x squared plus y squared. Okay. How about d on dx of d e of dw? Okay, so this is just 2x times z times 2w e to the w squared plus x squared plus y squared. So it's 4wxz e w squared plus x squared plus y squared. Yeah, they are the same. Why they are the same? No. The reason from the theorem. Yeah, because it's continuous, right? E is continuous everywhere, and then polynomial is continuous everywhere. Both of them combined continuous everywhere. So they are
So
continuous.
if we go continuous, then we don't need to come here.
But
A question asks you to find man, is it continuous? It doesn't give you man.
but you don't know the function, how you check the continuity at first. Unless you go through the original definition. Right?
Which is
Huh? Which is the limit?
I think the question will count.
No.
No,
Okay, unless the question said it is continuous, then ask you find both of them, you say by continuity, both of them. Unless later we will see. We need to what? No, you cannot check continuity. You cannot check.
then
So
why you do
so later we will use it to find extreme value, maximum value. Yeah. Yeah, like what you do in calculus too. You show that the second derivative is greater than 0, then it's a minimum, less than 0 is a maximum. Yeah, you have this similar version. Huh? What? What? Yeah. No, it's opposite. Okay. So what's del t del z? Sorry, del. Okay, you get 0. Actually, what's this this function here, right? W squared plus x squared plus y squared. This is what? If it is equal to some number, okay. But this value, what's this value? Something square plus something square plus something square. Linear algebra. Not quite. No, it's not the product. The product of what?
okay.
Too much. Length of a vector. Length of vector. How to compute length of vector? Yeah, square root of w a square plus b square plus c square. Okay. So actually this is the length. So you take e to the power of the length of the vector wxy, and then multiply with some number. This function. Okay. Okay. Yeah. Okay. I mean square of a length. Oh. Yeah. Square of a length. Okay. Okay, so how about show this? Show this. Okay, show this. So what are the first derivative you need to find first? Huh? No f here, leh. U, x, and yeah, del u over del x and del u over del y. Okay. Del u over del x is same thing. Okay, sure. Del u over del y. Okay. What else? Ex to the cos y times cos y. Okay. How about the next one? Okay. So differentiate again with respect to x of del u del x. You get same thing, right? Okay. Differentiate del u over del y with respect to y. What do you get? Minus ex over times cos y sin y. Okay. So you can see that one of them is just repeating, but the other one is like alternating. Okay. So if you add the two second derivative together, you get 0 because ex sin y minus ex sin y there cancel. Okay, so this is the Laplace equation. So anything that satisfies this Laplace equation is a solution to the Laplace equation. Okay, so this is one of the solution. Okay, let's talk about one more idea, then we can break. End class, yeah. Adjourn to next week. So, okay. So let f has a continuous partial derivative. So we can form something we call the tangent plane. Okay. So how we form this tangent plane? We use the two partial derivatives existed at that point. Okay. So remember, just now we have two slope, right? Just now we have two slope. Remember, at a point, okay, we can find two slope. Okay. So if we add up these two slope, take the linear combination of point, we will get a plane. Agree or not? Yes. Yes. Infinite. What? The plane is infinite. Yes, correct. Why? Okay. So, Indian. Okay. I mean, so you got a plane. So what's this plane for? Okay. So your tangent vector, right, lie from this plane. Right or not? Sorry. Okay. So just now you got this C here. Okay. And then you found the slope. Remember, we found the slope del F del S. Okay, let's call this point. What do we call this point? X naught, Y naught. So we call this point S naught, Y naught. Remember what we do just now? We differentiate F with respect to X. We differentiate F with respect to Y. Okay. And then we can evaluate this at a number. And then this number is the slope. Right. Slope. Remember the example just now. Let's go back to the example. See this example? Right. So we evaluate the partial derivative at a point, we get a slope. Okay. Yeah, we combine together, we take linear combination. We consider all the points as a linear combination of these two vectors. Huh? No need. It's a vector form. Vector form. Put T outside. Okay, so we consider a linear combination and then we form the plane. Okay, we form the plane. Okay. We can do example. Let me see. Example. Can do example, but you want to do now or do next time? Oh, okay. Okay, sure. But I'm not sure you can see the plane. Okay, sure. Okay. Let's use this example then. Okay. So my claim is we have a tangent plane. Z minus 1 equals to fx is minus 2 of x minus 1 plus minus 4 of y minus 1. Okay. Yeah, I'm explaining now. I'm explaining. Okay. So how we get this? Not plant plane. Okay. Tangent plane. So how we form the plane? What's the plane equation? We need to have the tangent and not tangent. The normal vector. Okay. Normal vector. So my claim is this fx fy become the normal vector with the z coefficient is 1. Okay. This is my claim. I claim first. Next time I show you why it's true. Okay, I claim first. The one that come out exam is you need to know how to find tangent plane. Okay.
Oh, so same thing lah.
What thing is same?
Then you find tangent plane.
Yeah.
So you're gonna teach half first next week, the other half.
Yeah.
Oh shit. Okay.
Oh, you wake up already. Yeah.
Yeah.
Okay. So how to find the tangent plane? How to find this tangent plane? We use fx, fy evaluated at that point, and then 1 as the coefficient of z. Okay. And then why we put z minus 1, x minus 1, y minus 1? We centered the plane onto 1, 1, 1. Remember, when we want to shift the center of circle, we also shift the x, y to the center. So we take x minus a, x, y minus b if the center is AB. Okay. So my claim is this is the tangent plane at that point. Okay.
So I have to find the simultaneous find the point.
No, you just find fx and fy. That's all.
How I know where the point is?
What do you mean?
Like chain like that, right? How I know which point is at? The one.
Oh, you need to find the tangent plane at. Okay, let me write down. Tangent plane at. Yeah, the point is given. Yeah, right, correct. Yeah, the tangent point at 1. Okay.
Okay, sleeping again.
Okay. Okay, so what's the normal vector of this plane? Last time you guys learned already, right? What's the normal vector? Careful. What's the normal vector? Not negative, 2, 4, and 1. Okay. 2, 4, and 1. Okay. What do you mean? Sure, but it's in the other direction. But it's still normal, right? Still normal.
Then you were asking from this point to this point.
Yeah.
So
This one direction. This one's still okay because normal we just want 90 degree. Normal we want 90 degree. Okay. So we got a plane here. So there's a normal vector to this plane, which is 2, 4, 1. Okay. So you can see that. What you can see. So the derivative becomes the normal vector to the tangent plane. Okay. Yeah. Why is it true? Don't know yet. Let's see next time. Yeah. Okay. So this tangent plane, there's a use of this tangent plane because in the surface, right? You're not only working straight or working sideways, right? Okay, you can work different way. Okay, when you work different way, they will have different tangent vector. Okay, you have different direction of tangent vector. So for example, if you like, you have these two directions for the moment, right? So if you walk different way like this, for example, okay. So if you walk like this, then maybe your tangent vector go this way now. Okay, but this tangent vector will lie inside this tangent plane. Okay, so meaning at a point there are two-dimensional function direction you can go. Okay, so we have this plane here. Okay, usually the dimension of the tangent is the same as the dimension of your surface or object. Okay, so if you imagine from one dimension, you got a line. Okay, you got a line. The only two direction you can go is forward or backward. Okay, so you just have tangent line. You don't have tangent plane in one dimensional. But two dimensional, you have tangent plane because you can go two dimensional. There are two dimensional direction you can go. Okay. So in this case, right, you should ask, can I differentiate with respect to different direction or not? Can I differentiate with respect to x plus y, for example? Huh? The answer is yes. You can differentiate with respect to any direction, which we will learn later, which is called the directional derivative. We can go different direction and then we differentiate through that direction, not just x and y. Okay. Yeah. Okay. Okay, we will repeat this again next lecture. I think there's a lot to repeat for your friend. Okay. Okay. So see you
when I
next Wednesday. Good luck in your exam.
这有看到是啊，很多人被他包括听到，是你就可以盖眼睛啊。
呀，
那边那个麦老师讲的。